This is Anthony Vaccaro at AppNIC 50 testing audio.
Hello again, everyone. Welcome back. This is Technical Session 3. I am Anna from APNIC, who will be your MC. Just a quick run through of the housekeeping. If you want to ask a question or write a comment, you can either use the raise hand function in Zoom and you will join the queue for voice question, or use the Q&A button in Zoom for text, and I will read your question or comment to the speaker. Please also be mindful of the code of conduct, which is published at the conference website and in the chat box. I'm sure you've already taken your good selfies while attending the session, so why not post them on Twitter or Facebook using the hashtag APNIC50. I am now giving the mic to our moderator, Masataka Mawatari from JPIX. Over to you, Masataka.
Hi, everyone. So my name is Masataka Mawatari from JPIX. I'm in charge of this session as a session moderator. So this Zoom room is for technical session 3 in APNIC 50. So we have 3 speakers in this session. It's full of all my favorite topics, and I hope that you like it. So first speaker is Mr. Devpan from ETH Zurich. We will talk about connecting the internet by satellite. It's a kind of recent topic. The title is Network Topology Design at 27,000 km/h. Please feel free to begin your presentation.
Thanks, Masataka. Can you hear me?
Okay.
All right, so let me share my screen.
Anything like trouble?
I cannot, maybe now. Okay. Hello, everyone. Welcome to my talk on how to design a network's topology when its components are moving at speeds of 27,000 km/h. Let me start by touching upon 3 fantastic recent advances in space technology. Reusable boosters, which come back to Earth after launching rockets, thus reducing launch costs. Significant reduction in size and weight of satellites, thereby packing more satellites per launch, reducing costs. And automated link tracking, which enables inter-satellite laser communication. Products offering laser inter-satellite connectivity at 10 to 20 G at distances up to 8,000 kilometers are already available. One caveat is that it takes a few seconds to tens of seconds to establish these laser ISLs. This will later be important when we discuss the various design challenges. But what are all these developments leading up to? The primary goal, it seems, is to build mega constellations consisting of thousands of low-flying satellites, which provide global low-latency internet coverage. SpaceX is leading the front. Their project is named Starlink, and they have already deployed more than 600 satellites in orbit. During the first phase, they plan to deploy 1,600 satellites and start providing internet coverage. Their long-term plan is to deploy tens of thousands of very low-flying satellites. Amazon is working on a similar project named Kuiper and plans to deploy more than 3,000 satellites in 3 phases, with each phase having slightly differing configurations. Various companies and startups have joined this race and have their projects at different levels of maturity. We here explore how to connect satellites with each other in order to build such networks and deliver traffic effectively. But first, a brief primer on the proposed satellite constellations is necessary to set the context. How do we describe a constellation, and what features distinguish this setting from traditional terrestrial networks? The first descriptive parameter I'll mention is altitude. A geosynchronous or geosatellite has a height of 36,000 kilometers, and the minimum round trip times or RTTs are nearly 240 milliseconds. Low Earth orbit or LEO satellites, on the other hand, fly at heights between 300 and 2,000 kilometers, thus reducing RTTs by more than 60x. Another descriptor is orbital inclination. Each orbit here has several satellites, while polar orbits traverse over the poles. Orbit can also be inclined. Inclination is the angle between the orbit and the equator. Here, the inclination is 53 degrees. Inclined orbits restrict satellites over densely populated lower latitudes. For polar orbits, the inclination is 90 degrees. Laser or radio links can be used between satellites, with laser offering higher data rates. Typically, there is a north-south, east-west connectivity pattern, which I'll refer to throughout as plus grid. To the best of our knowledge, all publicly available scientific papers, patents, and visualizations assume the same plus grid connectivity. A key feature of these constellations' promised connectivity is lower latency over distances beyond a few thousand kilometers. In this example, we are seeing a path between Zurich and Mumbai over satellites, which is quite close to the geodesic compared to fiber, which is roughly 2x longer. The speed of light being roughly 2/3 in fiber compared to free space means that the fiber path will be 3x higher latency. We'll refer to this inflation over geodesic, in this case 3x for fiber, as stretch. We compare the RTTs between the 8 most populous cities over today's internet to the estimated RTTs over a plus grid constellation consisting of 1600 satellites. The estimated RTTs are 70% lower than today's internet at the median. So if the current RTT is 100 milliseconds, the estimated RTT is 30 milliseconds. The estimates for the satellite network are a bit optimistic though. We did not consider latency inflation due to encoding, error correction, and other factors. But even a 20% increase in the estimate would result in the RTT of 36 milliseconds, which is still significantly lower than today's internet. We could also see from the plot that the latencies over satellite paths are very close to the geodesic latencies at the speed of light in vacuum. Let us now explore the system dynamics of these constellations. Satellites move fast relative to the Earth and with respect to each other. If a satellite is now over eastern Brazil, in 6 minutes, it will already reach Africa, crossing the entire Atlantic, traveling more than 500 kilometers per minute. Such highly dynamic behavior translates to links becoming infeasible in minutes. We should keep this in mind while exploring topology design and prioritize links which are available for longer periods. Having gone through the primer, we come back to the problem at hand. So how can we connect satellites in order to offer higher aggregate bandwidth, keeping in mind the dynamics of the system? I'll now discuss what are the constraints we consider and assumptions we make. The key constraint of this system is system dynamics. Satellites flying fast relative to the Earth and to each other. But we have other constraints as follows. Setting up links can take a few seconds to tens of seconds, during which time the involved communication units cannot transfer data. Hence, it's important to minimize changes in which links are connected. Also, the maximum number of ISLs per satellite is limited. In our work, we consider 4 ISLs per satellite following all recent FCC filings. But we believe our methods can be extended for other numbers. I'll also lay out the assumptions we are making in solving the intersatellite topology design problem. We assume that the satellite trajectories are given. We rely on FCC filings by SpaceX and Amazon that describe the trajectories. While trajectory design in itself is also an interesting question, we have not explored it in this work. Knowing what precise traffic will be served on these constellations is difficult. Our evaluation uses traffic matrices drawn from intuition, but the same approach can be used for arbitrary input traffic. Our focus is on the satellite-to-satellite connectivity. So we assume that the ground satellite connectivity follows a simple range-bounded model. We treat plus-grid connectivity, which I already touched upon earlier, as our baseline. On that last point, plus-grid being the baseline, what are we trying to improve? One drawback of these very local links to adjacent satellites is that one requires a large number of hops to reach distant destinations. On each hop, the end-to-end communication consumes resources, limiting the network's throughput. It does like to build networks that give short paths, but also admit high capacity. We don't need to stick to plus-grid's very local links. The key constraint on ISLs is for them to not dip into the mesosphere. This is the atmospheric layer that extends to about 80 kilometers above the Earth's surface, beyond which there is no water vapor present. Given the altitude of satellites, in this example 550 kilometers, using simple geometry, we can calculate the maximum permissible ISL length, that is about 5,000 kilometers here. This observation opens up a large design space. While at small scale, with few tens of satellites, only simple connectivity was possible, in the large proposed constellations, each satellite can now reach many more satellites. We are still restricted to being able to connect to only a few, though, limited by the maximum number of ISLs per satellite. In picking the particular subset of links to connect, what should we optimize for? We use simple intuitive traffic matrices for our evaluation. We picked the 1,000 most populous cities and use a population product traffic matrix. Let's CT1, CT2, and CT3 with 3 cities with different populations. The traffic between city pairs is proportional to their population product. We also tested a variant which relies on GDP instead of population. Recall that I earlier mentioned stretch and hop count. Stretch is the inflation in latency over the minimum possible, that is traveling the geodesic at the speed of light in vacuum. Hop count accounts for resource consumption and hence congestion. In this paper, we show that lower hop count translates to less congestion in these networks. We also define an aggregate metric as a linear combination of stretch and hop count, with alpha being the weight or importance of stretch. Superficially, this seems like a traditional network topology design problem. These are known to be hard even in static settings, but a variety of heuristics are used in practice. One key contribution of this work is showing why traditional techniques don't work here. We tried integer programming, but it suffers from two major shortcomings. It is limited in scalability. Runtime is greater than 2 days, even for 25 cities on a beefy machine, and the estimate is roughly 10 to the power of 29 days for 1,000 cities. But even if we manage to speed up the ILP by a large factor or use appropriate approximation techniques, there is a more fundamental issue here. The set of ISLs, minutes apart, are more than 90% different. We should remember that ISL setup times are few seconds to tens of seconds. So even if we could solve the problem optimally for a snapshot, the set of optimal links varies significantly minute to minute. Hence, to maintain optimality, the system would need to break and make a lot of links continually, resulting in significant disruption of connectivity. We also tried random graphs as they are shown to be useful in other settings like data centers. Although such random graph generation is faster, it also suffers from large number of links becoming infeasible within a few minutes. Regaining lost connectivity is not straightforward, and one would have to break and make many links. Additionally, random graphs are very inflexible and do not allow the operator to decide on the operating point. They simply yield one combination of stretch and hop count without any control over which dimension to optimize for. So where do we go from here? This, and this picture have something in common. They illustrate the use of structure and repetition for design, in this case, visual design. We apply the same idea of repetitive geometric structure to network topology design. Consider this 1600 satellite constellation. This is the field of view or connectivity for one satellite which goes beyond plus grid. A motif consists of 2 links with 2 other satellites, and this pattern can be repeated throughout to build the network. Note that in this case, 2 link motifs are sufficient, as remaining 2 would be filled by other satellites connecting to this satellite. One obvious benefit of using motifs is the fact that they have minimum link churn. Nearby satellites in adjacent orbits move together and are always in the field of connectivity of each other and can remain connected continually. We have analyzed 3 different constellations. A uniform 40-squared constellation consisting of 40 orbits, with each orbit having 40 satellites operating at an inclination of 53 degrees and an altitude of 550 kilometers. SpaceX Starlink Phase 1, which consists of 24 orbits, with each orbit having 66 satellites operating at 53 degrees and 550 kilometers. And Amazon Kuiper Phase 1, which is again a uniform 34-squared constellation operating at 51.9 degrees and 630 kilometers. Most of the results here are for the 40-squared uniform constellation. You can refer to the paper for the other results. Here we plot the average hop count along x-axis and average stretch along y-axis for the different motifs. Note that both stretch and hop count are weighted by the traffic matrix. In this case, population products for CTPS. Different motifs offer different trade-offs in stretch and hop count, and we can see a Pareto frontier of motifs superior to the rest in both hop count and stretch. Not only do motifs offer performance better than random graphs, they also provide higher flexibility to an operator. Note also that the random graph solution also suffers from link churn. So where is our baseline plus grid in all of this? This is where plus grid operates, with the best available stretch but very high hop count, thus being a low efficiency motif. Note that the slope of this frontier is small enough on the right side, such that by sacrificing 2% stretch, one can improve hop count by 32%. This is one of the resulting motifs for the 40-squared constellation that provides much higher efficiency than plus grid using a combination of long and short links of different orientations. I'm showing the two links in the motif in different colors here for clarity. So the motifs perform well, but can we do even better? Yes, by exploiting the geometry of these constellations. Compare the field of view of a satellite at the equator to one at a higher latitude. We see that the constellation is denser at higher latitudes. This translates to more options for connectivity as we go higher up from the equator. This plot quantifies the number of motif possibilities at different latitudes. For polar as well as inclined constellations, the number increases significantly with latitude. For example, for the inclined constellation, there are around 1,000 options at the equator versus around 3,500 at higher latitudes. So how do we exploit this characteristic? Consider a single orbital plane. A quadrant of the orbit consists of 10 satellites out of the 40 in total in this orbit. We split the quadrant into multiple zones, 3 in this case. Next, we find out the optimal motif for the entire constellation, considering only the motif possibilities available at zone 1. We assign the corresponding links to zone 1 and remove the rest of the links. We repeat the same process for zone 2 and then for zone 3. This is the final 3-zone multi-motif scheme for the 40-squared constellation we are looking at. As you can see in this plot, the multi-motifs offer a higher performance beyond the single motif frontier. Different alpha values result in different multi-motifs, and as we give higher priority to stretch, the schemes move towards plus grid. Putting all of this together, these are the performance improvements above the baseline plus grid connectivity. Starlink sees more than 2x improvement over baseline, while Kuiper also has similar benefits. We also considered settings where links need to be shorter due to power constraints instead of just the visibility constraint we considered thus far. In the most pessimistic case, a constellation must at least allow link lengths that suffice for plus grid connectivity. Even in this worst case scenario, Starlink sees a 40% improvement over plus grid. I'll now briefly note that this work is just one of several satellite networking problems we are exploring in our lab. As we discussed briefly, Kuiper, for example, plans to deploy 3 distinct shells which vary in inclination and altitude. We are currently investigating how to effectively connect these different shells for higher performance. Routing is very interesting due to the system dynamics, scale, and latency capacity trade-offs. Also, congestion control poses new challenges stemming from 2 reasons. Number 1, end-to-end path latencies change over time naturally, independent of congestion. And number 2, satellite path changes could result in significant reordering of packets. To help bootstrap research in this area, we're also developing packet level and flow level simulators that capture the necessary system dynamics. Thank you for your attention. I'll now be happy to take questions.
Thank you so much, Debupam. We are now open for questions. Okay, so if no questions, I am now handing back the mic to Masataka for our next speaker. Over to you, Masataka.
Okay, so let's move on to the next. So next is second speaker is Mr. Muhammad from DZCRD Networks. He will talk about network functions running general hardware with good performance. The title is PPS Matters, as you can see. Could you please start your presentation, Mr. Muhammad?
Thank you, Maotari-san.
Please go ahead.
Can you see my presentation?
Okay.
Okay, good afternoon, everyone. So my presentation is about PPS matters. Who am I? I'm mostly a FreeBSD developer and working as a FreeBSD courting secretary. Besides that, I'm a conference hopper and a consultant, mostly on network systems and larger scale FreeBSD deployments. So let's start with the basics, like what is a switch or a router? So a switch actually forwards frames based on MAC addresses, while a router forwards packets based on IP addresses. But there are something called a software switch or software router. So what are those? Those are just software-based implementations of a switch or router. Routers applications like PARD, FRR, Zebra, Quagga, or XBGP. Then there are software-based switches like Open-V switches. Those are mostly installable in a virtualized environment or on a NIX or Linux-based environment. So what is actually a hardware-based or hardware switch or router? Those are actually manufactured by the big name companies like Cisco, Juniper, Arista, Extreme, Nokia. Those comes with a really high price tag, sometimes comes with really big size and has different and multiple ports, like starting from 1 Gbps to 400 Gbps. 400 Gbps is already in a draft mode and we should be seeing it within a short time frame in the market. Besides that, there are so many jargons like ASIC or merchant silicon, then Gbps or terabit per second backend capacity or forwarding capacity. Then there is PPS forwarding, kPPS or MPPS forwarding, line rate forwarding, so many jargons to take care of. So what is an ASIC or a merchant silicon? One example is like ASIC miner. If you have heard about Bitcoin mining, then you know that the hardware used is the hardware that is used behind Bitcoin mining is an ASIC miner. So ASIC is application-specific integrated circuits. Some of the applications are like Bitcoin mining or voice recording, cryptographic acceleration or network switches or firewalls. The new lingo for the data center switches is silicon. Those are off the shelf or sometimes custom built ASICs. There are multiple vendors like Broadcom, KVM, who manufactures these silicons. Broadcom Tomahawk is one of the flagship ASICs, which is used by Amazon for their switches in their DC. This is the basic architecture of a Tomahawk 2 processor. It has a capacity of 6.4 terabit per second packet forwarding in a single chip Ethernet switch. It has got 4 pipes of 1.6 terabit per second. There are lots of buffers. There are 64 Falcon cores and 1 Merlin core. So you can see in the bottom like how many serializer and deserializer are used to connect Ethernet interfaces. It also comes with ingress and egress packet time stamping. So now the big question, if there are open source switches or routers, why do we need to buy a highly price tagged vendor devices? Or why use silicon or chips instead of a generic x86 processors? Or like if Unix or Linux can do anything, why don't you install those applications and get rid of hardware vendors? So what is the basic difference between x86 versus an ASIC? So there are lots of terminologies here. So an x86 processor is actually a jack of all trades, but master of none. There are lots of CPU and PCI interrupts. There are limited PCI bandwidth and based on CPU architecture. Then there is FPGA, which stands for field programmable gate array. which is a master of one, and it is field programmable. That means that it can be programmed outside of a factory. It usually gets programmed once, and this process can be described as like setting up its internal structure. After the process, it behaves like a tiny computer specialized for only one specific purpose. Then there is the ASIC. We have already talked about it, the master of one thing, and there are no interrupts, and the PCI bandwidth is huge for that. So it is actually the ultimate specialist. It is a chip designed and produced for one and only one task, a task it does extremely fast and very efficiently. There is no possibility to reprogram an ASIC. It leaves the facility or a factory fully defined, and it's useless when its job is no longer required. So designing ASIC is something only large scale corporations can afford, because debugging them is really difficult. So if you think in number of cores, then look at in this way, like your laptop computer or your desktop computer have at least maybe 4, 6, or 8 cores that can do everything. But ASIC, they have got thousands of cores, very teeny ones, and capable of one thing only. There are some more into it, like POSIX. POSIX is Portable Operating System Interface. So POSIX sockets evolved early in the days of the Berkeley Unix solutions and evolved from Berkeley sockets. So BSD sockets are still a de facto standard since the 4.2 BSD Unix system. It was more adapted from Unix to Linux and then to Windows. The basic life cycle is like socket, bind, listen, accept, send message, and receive message. The network stack is mainly implemented in the kernel, so the functions are using lots of system calls, and the system calls create the higher overhead for context switching and CPU cache pollution. So the game is like back and forth, and we have got multi-core CPU and multi-queue NIC, so this goes on and on. Besides that, the socket buffers or network memory buffer stresses the operating system's memory allocators a lot. Here are some interesting calculations we need to understand. There is actually a gap or pause required between the packets or frames when it is sent from one into another. This is called interpacket gap or interpacket frame spacing or interframe gap. The standard is 96 bits of times. So for a 10 Mbps Ethernet, we require 9.6 microseconds. So this is how it goes on. And if we look at it like for 100 Gbps connectivity, it requires around 0.96 nanosecond of gap in between the frames or packet to be sent or received. So more into it, like when it hits the kernel, what happens? The kernel processing time for 138 bytes of frame at 10 Gbps, it stands at 1230.4 nanosecond between the packets and reaching at 815 kbps or kilopacket per second. At 40 Gbps, it is 307.6 or 3.26 Mbps of packets we can achieve. At 100 Gbps, it is like 8.15 Mbps. So if we consider the smallest frame size of 84 bytes at 10 Gbps, it comes around to 67.2 nanosecond between packets, which gives us the highest possible capacity of 14.8 Mbps traffic. For the 67.2 nanosecond gap, we require a 201 cycles CPU cycles if the CPU is running at 3 gigahertz. So there are OS limitations. Most OS are jack of all and master of none, like the desktop. Then there is mail server, a web server, DNS server, so many things. Then we can use it for graphics rendering, gaming, or our day-to-day work. They are not designed for performance packet processing at all, and not optimized for line rate packet processing. There are a few of the routers which are capable of doing it, like Viata or BSDRP. There are lots of other commercial OS, but this is not the end game. We can do a lot more than this. So we can look into kernel bypassing. So what happens when we want to bypass the kernel and stack our networking part in the network card rather than the kernel? So here we have a kernel networking stack and the kernel bypassing stack. So in the bypass, we have lots of technologies like RDMA, TOE, or TCP offloading engine, open unload, DPDK, VPP, or some other technologies that might come in the future. And there is the application, the OS, the user space or the user is using. zero copy actually has a significant importance here. So while zero copying, the CPU skips the task of copying the data from one memory area to another, saving the CPU cycle and saving more memory bandwidth. There are lots of OS elements like device driver, file systems, or network protocol stack. It reduces the number of mode switching between the kernel space and the userland application space. So mostly uses raw sockets with a memory mapping, and kernel bypass utilizes the zero copy, and they are not actually the same. Here is one of the technology called RDMA, or remote direct memory access, implemented over high-speed loaded network fabrics. The direct access to remote host memory dramatically reduces the latency and CPU overhead, requires a specialized hardware like a special NIC with support for RDMA technology. It bypasses the remote or local operating system and transfers data in between where an application memory directly. It also bypasses the CPU cache and context switching because the network interface card actually takes care of this. It transfer continues parallelly with the OS operating without affecting the operating system performance, and the applications can or cannot be RDMA aware. There are some more in-depth description of RDMA, but I will not go into this. This is just for your reference. Then there is ROCE, which is RDMA or Converged Ethernet. There are two versions, one focusing mainly on Ether type 0x8915 or maybe working at layer 2. The other is version 2, which focuses mainly using on UDP or IPv4 or UDP with IPv6. There are lots of variations of these, but we will also not go into more into this. And I'll just mention that some of the vendors are like NVIDIA, were Mellanox, and Mellanox was bought by NVIDIA recently. Then there was Emulex, which was bought by Broadcom. There was QLogic or Marvell, which was took over by Cavium. So let's go to the very basics of internet, or how connection works. Connection establishment, like SYN, SYNEC, or ACK. So there is acknowledgement of traffic receipt, there is checksum and sequence, then there is a sliding window calculation, then there is congestion control, and there is connection termination. So how are these being used? The TCP offloading engine offloads kernel TCP stacks in the NIC cards rather than the operating system kernel. It frees up lots of host CPU cycles or the XSS processor CPU cycles, which reduces the PCI traffic in between the PCI bus of the hardware and the host CPU. There are lots of different types, like parallel stack full offload, which where the host over TCP IP stack and parallel stack with the vampire tapping. Then there are HPA full offloading or host bus adapter used mainly in iSCSI adapters. So besides TCP, it also offloads the iSCSI functions, giving higher throughput for storage systems. Then there are TCP chimney partial offload. This is the main Microsoft lingo, but mostly used alternatively of TCP offloading. The selective TCP stacks are offloaded using this technology. There is TSO or LRO. TSO is the TCP segmentation offload. Big chunks of data when are split into multiple packets by NIC before transmission, depending on the MTU of a link in between the networking devices. The NIC calculates and splits the data when offloaded from the host operating system. The LRO is just the opposite, and multiple packets of single stream are aggregated into single buffer before handing over to the host operating system, reducing the CPU cycles. Checksum is very important, although very weak check is compared to modern checksum methods, but TCP needs more error checking, uses one of the once complement algorithm. This is a highly CPU intensive work, but it can be offloaded into NIC card if supported too. It has also some disadvantages, like if used along with some packet analyzers like Wireshark or TCP dump, it will report invalid checksums for packets received. And if used with some virtualization platform, it do not have checksum offload capacity in the virtual NIC driver, then also it will report invalid checksums. There are some ecosystems or software applications.
Sorry, I think you lose your volume or your voice audio, Moinor. Moinor, we can't hear you.
Then there are XDP or Express Data Path. It is in the kernel, Linux kernel 4.8. It is an eBPF-based high performance data path. Similar to AF packet, a new address family like AFXDP. It's only supported with Intel or Mellanox cards. eBPF is also offered to NIC in case drivers are unavailable, and this is 50% performance very slower. 26 Mbps of per core drop test has been checked successfully with commodity hardware. This is not kernel bypass, but rather integrated fastpath in kernel. Then there is DPDK or data plane development kit. The set of data plane libraries and NIC drivers maintained mainly by Linux Foundation, but it is BSD licensed. There are lots of programming framework for x86 and ARM processors. There is an environment abstraction layer, which is created consisting of a set of hardware software environment. There are lots of hardware that supports it, mainly AMD, Amazon, Quentia, Atomic Rules, and lots of those. This is extensible to different architectural systems like Intel IA32 processors and FreeBSD operating system.
Munir, sorry, we have to interrupt. We have 1 minute left for the presentation.
Okay. Okay. I'll just go through one novel framework, which is NetMap, a very fast packet I/O mechanism between the NIC and user space. It removes lots of unnecessary metadata allocation. It's supported both in FreeBSD and Linux observable kernel module. It comes default from FreeBSD 11 and released under BSD 2 close license. Lots of supported hardware like Intel, Realtek, and Chelsea. 14.8 Mbps traffic has been achieved in 10G NIC with 900 MHz CPU. Here are some examples of how we can do FreeBSD, kernel bypass and FreeBSD. Here's an example of how NetMap performs over other high packet rate applications like Linux and FreeBSD. Here are a couple of real-life scenario of FreeBSD, like we are using for VM and jail traffic bypassing. Then we are using for IDS and IPS with high traffic using NetMap for DDoS detection, lots of things. There are a couple of other ecosystems like OpenOnload, Napatech, and PFRing. So here are the examples. So that will be all from here. I'll take some questions if there are any.
Thank you for wrapping up the presentation, Munir. We are now open for questions. As a reminder, you can either raise your hand and I will unmute you, or you can type your question in the Q&A. Okay, so if no questions, I am now giving back the mic to the moderator, Masataka-san.
Okay, so third speaker is Mr. Jeff Houston from Epic. His talks are always most suggestive. So today's title is DNS and IPv6. Please start your presentation, Jeff-san.
Thanks a lot for that. Let me bring up a desktop and 1 second. And we're sharing. Hopefully you can all see that, otherwise shout at me. So this is a talk about DNS and V6. What it's not a talk about is DNS over HTTPS or DNS over TLS or DNS over QUIC or anything else. Now, it's true that DOE, DNS over HTTPS, is the hot topic in the DNS. And, you know, there's so much more that can and will be said about DOE and DOT and all those other encapsulations. That's a great talk, but it's not this one. We're going to talk about an oldie but a goodie. And oddly enough, even after, 25 years, V6 still gives us surprises. And in some ways, that combination of V6 and the DNS is actually not that well understood. So I'm going to ask 3 questions in this talk that sort of talk about how well is V6 actually supported? What happens in dual stack mode? Do we do happy eyeballs? If we actually did a V6 only service in the DNS, how many folk couldn't get there? And lastly, because DNSSEC is important and we should all be doing it, How well does v6 support DNSSEC, and in particular, large answers? So just before we get into this, let me firstly say, we really, really, really don't understand the DNS. The DNS is a bunch of resolvers. What's a resolver? Something. It could be a machine running a program, or a bunch of machines running a bunch of programs, or a bunch of switches or caches, or all kinds of things. And a resolver might have one client, me, or, you know, a few billion clients like Google. So we actually don't understand the word resolver. That's confusing. We also don't understand the concept of a query, which again sounds silly, but quite frankly, queries in the DNS are odd, because this whole distributed resolution process, one query comes in, lots of queries come out. There's this whole issue of discovery, retransmission, timing, etc. Queries don't even have a hop count. I'm sure that if you looked hard enough, you would actually find the DNS query, or maybe 10, or maybe a million, endlessly being forwarded around tight little circles on the internet. They have a life of their own. So on the understanding that we really don't understand the DNS, and we don't, let's move on and actually look at this. So we're actually making a large-scale measurement system. I've talked about this enough that I won't spend time on it here. But the basic answer is, to find out how users do things, we actually get users through an advertising system to insert known queries into the DNS at the edge. All those queries go back to authoritative servers that we operate in the middle, and we look at the queries we get and infer behavior of the DNS in the middle. So the first question, how well does DNS actually handle dual stack? Is there happy eyeballs? Now, happy eyeballs is actually really important, because happy eyeballs says, if you can do v6, you should prefer to do v6. Why is that important? Because we actually don't know when to turn off v4. No idea. But one of the best ways of doing this is, if everyone does happy eyeballs, then v4 will naturally die, because as we roll out more and more dual stack, and as applications prefer to use v6 in a dual stack world, then v4 just dwindles and disappears. So that's why it's an important question. And if the DNS doesn't use happy eyeballs, we should get sad, because that would be bad. That would actually make the whole transition more difficult, because no one knows when to turn v4 off. And worse, is there even a reverse bias that rather than preferring 6, do we actually prefer 4? We did a few hundreds of millions of tests, a lot of tests. And this is the capability of users. So 67% of users only ask using v4 only in dual stack mode, 2/3. 15% in v6, and 18% do a bet each way and actually ask us the same question in 4 and 6, well, because. So here's the graph over time over 2 years. v4 only is at the top. September 2018, 85%, even some days at 90%. A few months ago in July, when I did this slide pack, 67%. So that's good news in terms of v4 only is slowly declining. What about v6 only? Well, it started at 10%, but it's only climbed up to about 16%. The rest is, oddly enough, asking us both protocols at the same time, that green line. So let's look at that green line a bit, because we're seeing the same query in 2 different protocols at once. We sort out which one hits us first. Is the first query in v4 or the first query in v6? By a slight margin, v4 is the winner. That even when the user can support both protocols, the first question asked is in v4. Small bias to v4. So that kind of gives us the first answer. Is there happy eyeballs? No. Sad face. Is there reverse bias to use v4? Well, yes. Not good. For transition, probably not the best answer. Okay, the next one, v6 only. Again, lots of tests. This thing only answered in v6. If you asked us over v4, no answer. Oddly enough, a bunch of people, about 15%, in fact, sorry, 20% of folk who only asked us using v4 in dual stack actually had v6 tucked away in the background. 55% of users actually managed to ask us the question in 6, which means there's actually quite a bias to 4 in a dual stack world, not a bias to 6. So good, but not brilliant. That number, by the way, 55% of users, is a lot higher than v6 all the way to the end users. We're around about 28% of end users able to use v6 for, you and I as end users. The DNS is higher at 55%. The penetration is greater. But like I said, the lack of happy eyeballs probably compensates a bit. So comparing the two, that's what you've seen so far. So the answer for the second question, a little over half the users. So if you mounted a v6 only service in the DNS, expect not to see half the internet. Hopefully that number will get better over time. And last and not least is the real question, because DNSSEC is important for the DNS. It's important for the internet. Being able to believe what you hear in the DNS is actually really important because attacks get better. The whole issue of fooling you by giving you the wrong answer in the DNS is still a tried and true method for being naughty. So DNSSEC is useful, but DNSSEC is big. Now, I don't know how many of you have gone deeply into v6, but what you actually find is packet fragmentation changed. In v4, fragmentation is a part of the v4 header. So routers, end systems, anyone can actually fragment a packet. That's what v4 is able to do. v6 did two things. It changed the header and moved it into an extension header, so that when you actually fragment a packet, you insert something between the normal header and the payload, the TCP payload or UDP, you insert a fragmentation extension header. Everything else gets pushed down. And secondly, the don't fragment bit in v4 is jammed on in v6 and you can't set it off. So only the source can fragment, no one else can. Now, you might say they're minor changes. I would actually argue they were fundamental changes to the way the protocol worked and have been the source of almost all of our v6 deployment headaches. Well, maybe not all. There are a lot of deployment headaches, but this is one of them. So who uses fragmentation anyway? Mark, why are we talking about this? If you did a dig for the DNS key, the DNSSEC keys of .org, the answer was 1625 octets, bigger than almost any path MTU on the internet. So if you wanted to query .org, you got a fragmented answer. I use this example a lot. It's a great example. .org's very common. The good folk at PIR who do the registry for .org kind of got the message. It took them a while, 3 years, but when they got the message, they went and changed it. And now when you dig .org, the answers are much more modest, 1058 octets. So .org has fixed itself. So the problem's gone away, right? Well, no, the problem's still there. Because when we opened up the route for all these new GTLDs, we actually insisted that they're all DNSSEC signed. And they used hardware that did indeed get enthusiastic about packing signatures into the DNS key responses. So here's the few of the biggies. American Express has a DNSSEC key, and if you ask for it, 2,972 octets. Fragmentation City, here we come. And as you see, it's not the only one. And indeed, there are about 300 of these GTLDs in the root zone alone that actually rely on UDP fragmentation to get the answer back to you if you're going to use UDP. So fragmentation is actually really important, but doesn't work very well. There are firewalls that hate fragments. In v6, you've got to do ICMP diagnostics, which means firstly, you've got to accept ICMP messages. Not everyone does. And secondly, of course, you've got to figure out what to do with it. And in UDP, ICMP6 processing is a nightmare because unlike TCP, you don't hang on to things, you just send it. It's UDP, it's stateless. So what do you do when you get an ICMP packet too big message? I don't know. A lot of operating systems don't know either. Last and not least, it's implemented in extension headers. Extension headers are evil. So many switches. If you want really, really high speed, as we saw in the last talk, you have no time to unravel an extension header. And if you're actually doing switching based on a 5-tuple that includes the UDP or TCP header, you're toast. It won't work. So extension headers cause their own forms of packet drop in V6. So UDP fragmentation is pretty sick. So let's see how sick. Can we measure it? Of course we can. We use the ad network. We actually send back big answers that intentionally fragment. We did it back in April of this year. So this is a pretty recent stat. 27.6 million times, failure rate 11.2. That's 41%. I don't know about you, but if I was bringing up a service that had a 41% failure rate, that's not just bad. That's awesomely bad. That's horrendous. So what are we going to do about it? Because we can't say, don't run DNSSEC. That's not an answer. Well, we have to run V4 because V4 does fragmentation so much better than V6. Yeah, right. So what are we going to do? Do we fix it or work around it? What do the RFCs say? Because obviously every question's answered by an RFC these days. So here's one, March 2017, done by, some folk who are meant to know what they're talking about. This is 8085. It's a BCP, so it must be true. What does it say? Don't fragment. Oh. But I thought we relied on it. Whoops. So what are we going to do about this? We can try and get every single deployed router, switch, firewall, and everything else to actually accept packets with IPv6 fragmentation extension headers. Good luck. Ain't going to happen. The pig is off there in the air. It's not flying. Unfortunately, we've gone so far down the path, you can't change the way the network works anymore. It drops extension headers. That's life. Well, let's not use extension headers. Let's put it back in the V6 header. Let's change IPv6 because, it's only 25 years down the track and, we really haven't implemented it. So, of course, we can change it. You thought flying pigs were bad. Obviously, this isn't an option. You're down between a rock and a hard place. And about all that's left now is not to fragment at all. We can't. It doesn't work. Because any of those other options are pain, cost, and inconvenience. But even avoiding it is pain, cost, and inconvenience. So somewhere we're in a sort of a bad place now, and the answers aren't clear. But we are getting more because we're endlessly inventive. This whole UDP thing, bad idea. Let's just do DNS over TCP and walk away because TCP can handle all this. Of course, the DNS will melt. Because UDP is such a fast, lightweight protocol, we actually make the DNS work because of UDP. If we had to do session states everywhere, it's not clear we could do it for the same price. We can do it, but it'll cost more. Who's going to pay? Don't know. Well, if we're going to do TCP, we might as well encrypt it. So let's do TLS. And if we're going to do TLS, why don't we frame it up with HTTP? And if we're going to go down that fashionable path, geez, let's just use QUIC because, we can. Or do we actually get a new DNS framing protocol because we obviously can't recycle any of the others? I suppose they're options. I think they're all crazy to some extent as the default. As the default for everyone, none of these really give us the economics of the DNS we have today. They all cost. So what other option is there? You can try and change the application itself, do UDP MTU discovery. You could shift those additional records out. You could bloat responses elsewhere. You could, but no one's going to do that. So what now? Well, we know the problem space. That's good. Knowing what problem you're actually facing is actually half the battle. We'd actually prefer a plan that allows each of us to work independently. Because while there have been DNS flag days, and I'll talk about it again at the end of this slide, Getting everyone to do the same thing at the same time on something the size of the internet? Yeah, right. We can't make fragmentation and path signaling work in the V6 network. Give up. We can't get rid of all those filters. We can't make extension header packet droppers work. If you want speed, you can't make extension headers work, full stop. So you haven't got an option that way. And we can't change the V6 protocol. That's just not an option. So we're probably looking at changing the DNS again. And that burst of enthusiasm that gave us large fragmented packets, the eDNS0 UDP buffer size, and the default setting of 4096 octets was hopelessly optimistic. And so now there's a flag day coming up. A second one, because the first one was so good. The second one proposes that DNS software uses an upper limit on the UDP buffer payload size of not 1500 octets. No. 1232 octets. That's your lot, which is going to be uncomfortable because that's going to cause an awful lot of odd behavior for folk that don't like doing DNS over TCP. Because if you can't cram the big packet in UDP, you get back a truncated answer and your only choice then is TCP. So it might have started as DNS over V6 and the whole lack of happy eyeballs, which itself is sad. But it turns out that DNS and V6 really are that incompatible that we actually have to revise some of our views around large packet behavior in the DNS and actually strip out some of the more optimistic uses of UDP that kind of worked in V4, but will never work in 6, and just stop using them altogether. Thanks for this. Time is running out on us, so I've left a couple of time for questions. The pack that I've actually uploaded has a whole bunch of extra slides that names the guilty and talks about who's not doing which, including, by the way, Google. So if you're listed there, yeah, right. Not the best of ideas. So I'll happily take some questions. I think we've got a couple of minutes left. Thank you.
Thank you so much, Jeff. So are there any questions for Jeff?
Oh, come on. I've just trashed V6. Isn't anyone going to say anything in its defense? But it's really good protocol.
I don't see any questions, Jeff, so far.
I see. We all agree. Just don't tell the V6 session tomorrow. Don't tell them.
Okay.
Okay, I will stop sharing then. And like I said, no one's prepared to defend it.
All right, so if no more questions for Jeff, I'd like to thank our presenters, Debopam, Moinur, and of course, Jeff, and also our moderator, Masataka-san. I'd like to invite you now to participate in the poll for this session. It should be coming up on the screen right now. There you go. So this is the end of technical session 3, and I hope you can all join us in the virtual social, which is available in the conference program. See you guys.
Thanks all. Bye.
Thank you all.
Don't let the little time sounds really catching on.